You know, Intel has a history of making these massive, gutsy bets on new technology. I mean, from stretching silicon atoms to get more performance, all the way to the 3D FinFET transistor, they've just never been afraid to take a really big swing. So today, we're going to dive into their next one, a breakthrough that's less about just shrinking transistors and more about completely rewiring them from the ground up.
And yeah, that quote really hits the nail on the head. The upcoming 18A process node from Intel, it's not just another small step forward. We're talking about a fundamental change in how chips are even built. This is Intel swinging for the fences with a technology called backside power delivery. So let's break down what that actually means.
All right, here's the game plan. We'll kick things off with why Intel is making this huge bet in the first place. Then we'll get into the fundamental power problem that all modern chips are facing. We're going to see why the old way of doing things is failing, uncover the radical new solution, walk through the absolutely mind-bending way they manufacture this stuff, and then, finally, look at what this all means for the future of computing.
So let's get right into it. Intel's next big swing. Now, a lot of the chatter you hear is about new transistor designs, things like gate-all-around. But there is another, and I'd say equally critical, innovation happening at the exact same time. And it's that second one, the Backside Power Delivery Network, or BSPN for short. That's our focus today. Now, it might not sound as flashy as a whole new transistor design, but I would argue it's the more electric of the two. Because it solves a problem that has been getting worse and worse for decades. To really get the solution, you first have to understand the problem. And it all comes down to a simple question. How do you feed trillions of tiny little switches the exact right amount of power all at the same time without anything blowing up? The easiest way to think about voltage is to picture it like water pressure in a pipe. It's the force that pushes electricity, the electrons, through all those microscopic wires inside a chip. And just like the plumbing in your house, that pressure has to be absolutely perfect.
And this is what the source material calls the Goldilocks problem. If the voltage is too low, the transistors don't switch on and off when they're supposed to. That leads to calculation errors, or worse, the dreaded blue screen of death. If it's too high, the chip just guzzles power, gets way too hot, and can, literally fry itself. It has to be just right, and we're talking within an incredibly tight 5 to 10% margin.
So this massive, unbelievably complex system, all the microscopic wires, the voltage regulators, the capacitors that have to pull off this amazing balancing act, that whole thing has a name. It's called the Power Delivery Network, or PDN. You can think of it as the chip's entire circulatory system. And right now, that system is under some serious strain.
And that brings us to the heart of the issue. As we cram more and more transistors onto a chip, the traditional way we've built this power delivery network is hitting a literal wall, a wall of resistance.
Okay, so meet the villain of our story, a phenomenon called IR drop. It's pretty simple, really. As electricity moves through any wire, the wire itself has a natural resistance, and that causes a little bit of voltage to get lost along the way. Think of it like a dam that slightly lowers the water pressure downstream. On a modern chip, with billions of transistors, this isn't a tiny leak anymore, it's a major problem.
And this right here, this is the problem in a nutshell. For decades, the wires that carry power have been built in the same layers, right on top of the transistors, as the wires that carry the actual data signals. So you've got power and data all fighting for the same incredibly limited real estate. It creates this microscopic traffic jam.
And to deal with this jam, the only solution was to make the lanes, the wires, narrower and narrower. We're now down to just 20 nanometers wide. But at that tiny, tiny scale, even a great conductor like copper really struggles. It's like trying to force a fire hose worth of water through a drinking straw. The resistance becomes immense, and the whole system just starts to choke. So, okay, the old method is clearly hitting a dead end. You can't just keep shrinking the wires forever. You need a completely new way of thinking, and that brings us to the breakthrough. And the solution is one of those brilliantly simple, why didn't I think of that ideas? Instead of having the power lines and the data lines fight for space on the front, what if you just moved one of them out of the way entirely? The big idea here is to take the entire power delivery network and move it to the backside of the silicon wafer. You completely separate them.
I know. That sounds like something straight out of science fiction, right? Moving all the power lines to the back of a chip? So the obvious question is, has anyone actually tried something this radical before? Well, believe it or not, the answer is a resounding yes.
The core principle behind this has actually been used for over a decade in the camera sensor that's probably in your pocket right now.
So let's rewind a bit to 2009. Companies like Sony figured out that the wiring on top of their image sensors was literally blocking some of the light from getting to the pixels. Their solution? Backside illumination. They just moved all the wiring to the back. It first showed up in the iPhone 4, and today it's totally standard. So this proves the basic concept isn't just possible, it's been a commercial success for years.
Okay, so the concept is proven. But taking that idea from a relatively simple camera sensor and applying it to a ridiculously complex logic chip with billions of transistors, well, that requires a manufacturing process with a level of precision that is almost unbelievable.
All right, buckle up, because this process is just wild. First, you grow some special layers on your main wafer. Then, you take a second blank carrier wafer and literally bond it right on top. Now here's the crazy part. You flip the whole sandwich over, and then you grind down the original wafer until it is just 500 nanometers thick. I mean, that is just astonishingly thin. After that, you have to edge these perfect microscopic tunnels called vias through that thin silicon to reach the transistors below, and then you fill those tunnels with metal. It's an absolutely incredible feat of engineering.
So you go through all that insane, mind-bending work. What's the payoff? Was it all worth it? This is where we see why this is such a game changer. Oh yeah, the results are huge. Remember our main villain, IR drop? Well, studies show it gets reduced by a factor of 7. That is a massive, massive improvement. It also leads to around an 8% drop in total power consumption. And because you've cleared out all that power wiring from the front, the signal wires now have more room to breathe, which means they can run faster. It is a win-win-win.
And this, of course, brings us to the big race. As you can see, Intel is going all in, targeting 2025 for its 18A node that features backside power. Its biggest rival, TSMC, is being a little more cautious, and they're planning to introduce their version a year later, in 2026. So, if Intel can actually hit its schedule, this could give them a pretty significant performance lead in the market.
Look, at the end of the day, this isn't just some small, incremental step. By literally opening up the backside of the wafer, engineers have added a whole new dimension to chip design. This paves the way for all sorts of new 3D stacking and integration that just weren't possible before. So this isn't the end of a trend. It's really the start of a whole new era. And the real question is, what are we going to build with it?